Okay, we're recording. So, drag force. Drag force is the special name for friction that is not constant. So, we are going to start with an example of, let's see, what shall we make this object? This is a car. Driver just took their foot off the gas pedal. So I want to draw a free body diagram. Foot not is on the gas pedal and it's not on the brake pedal. What are the forces on this car? Force of gravity, straight down. What else?
Well, what do they call it force but the engine?
Well, but the engine's not doing anything because he's not pushing on the gas pedal. So the engine is not active.
So friction.
So we're going to have a normal force. And then instead of labeling it a friction force, I'm going to label it a drag force. And this drag force is modeled by some constant that depends on the car times its velocity. So when the driver first takes his foot off the gas, there's a fair amount of drag force because he's got a pretty high velocity. But as he slows down, there's less and less drag force. So there's going to be, he'll still be accelerating, he'll still be slowing down, but the rate of acceleration will be changing. So we don't have a nice simple expression for the acceleration is a constant value because the acceleration is going to depend on how fast is the car going right now. Now I put the negative sign on here because this drag force is in the opposite direction of the velocity. The car is moving to the right, the drag force is to the left. So if you want to actually add the vector symbols on here, that's why there's a negative sign. Okay? So I start from Newton's second law. That acceleration, I don't want to write it that way. I'm going to start with net force equals mass times acceleration. And so of the three forces, what is causing the net force? Only the drag force. So I'm going to write on this side negative b, and then I don't know why I wrote curly v there and regular v here, but I did. And then I'm going to make a substitution. How is acceleration related to velocity? Acceleration is the rate of change of velocity. And if it's a continuous change, we have to use calculus. Acceleration is the derivative of the velocity. So this is called a differential equation because there's a derivative inside an equation that includes the thing we're taking the derivative of. So this is next level of calculus. I didn't encounter this until my second year of calculus when I took a class. So the first year of calculus is single variable calculus. I learned all about derivatives and integrals. The third semester of calculus that I took was called differential equations, and this is one of the ones we did. So this, thankfully, is what's called a separable differential equation. So the technique that you use is I'm going to put all the v stuff on one side, and I'm going to put the other stuff on everything else on the other side. Okay? So I want to move this v to be with the dv. So I'm going to have dv over v. And then I want to get rid of the m and the dt. So I'm going to have negative b dt divided by m. Any questions on my algebra? So because I'm almost positive, y'all haven't seen this in calculus yet, have you? I didn't think so. So this is one of those things, well, why did you do it in that order? Because this is what works in calculus. It's a technique you'll learn in the calculus class. Now, here's what's cool about this. I can integrate both sides of this equation. So I'm going to write my integral symbols. But I need to know when I'm integrating from and to. So our goal is to eventually write an equation of velocity as a function of time. That's how we're trying to separate out this relationship. So the initial velocity of the car, so this is right when he takes his foot off the gas pedal, his velocity is VO. At some later time, his velocity is going to be V. Now this is bad calculus notation, but calculus teachers do it too, because I'm saying I'm integrating with respect to V and then my final thing is gonna be V. Just go with it. Sometimes they'll add like primes to indicate the difference, but it's fine. And then on this side, I'm integrating with respect to T. Well, my time starts at 0, and then I wanna know the velocity at this later time. Okay? So now, performing the integral is actually not that hard. B is a constant that depends on the car. M is the mass of the car. That's a constant also. The only thing, so I can pull out minus B over M. And then what's the integral of a derivative? Like, what's the whole point of doing integration versus differentiation?
It's the power up with the integrals, and then with the derivative, it's power down.
So it is a power up. Another way you can say it is that the integration cancels out the derivative, and so we're just left with T. Okay? And then we need to evaluate that between 0 and T. On the other side of the equation, all we have is dv and v divided by v. We don't have any constants we have to worry about. Calculus people, have you done this one yet? What's the integral of dx over x? No? That's the other direction. That's the second derivative. This is actually the natural log of v. And I would point out that's on the formula chart. Here we go. So the integral of x in the denominator is the natural log, and then they added a constant to it, so it's the natural log of the thing plus the constant. Okay? So, natural log. Now we substitute in. And some of this may seem a little trivial, but, okay, we do b over m. So I need to substitute in t for t, which is silly, minus negative b over m, and I need to put it 0 for t. So this whole term goes away. And my left side is just bt over m equals. Over here, I need to do natural log of v minus natural log of v naught. Okay, so everybody remembers this is the fundamental theorem of calculus. The first one or second one I never remember. But after you integrate, you plug in the top number and you subtract out the bottom number plugged in. Now for this next line, what do you remember is cool about subtracting natural logs? Or any logs. We can put these together into one natural log. Does anyone remember how? By dividing, very good. So this is the natural log of v over v naught. Okay? So we're going to pause, review, then we'll go forward because where are we headed with this whole thing? We started off with this force that depends on v. So the acceleration, the rate of change of velocity, depends on the velocity at that moment. We're trying to find an equation that's v by itself as a function of time. We've done that, but it doesn't look pretty. I want to finish solving this to have v by itself. So I need to get it out of the natural log. What's the inverse function of log, of natural log? E, yes. So we're going to raise both sides e to the power of. So on this side, we're going to have e to the power of negative bt over m. And on this side, we're going to have e to the power of natural log of v over v naught. Well, e to the ln cancels out. So we're almost done. E to the negative bt over m equals v over v naught. So what's my last step to isolate v? Multiply both sides by v naught. So v of t equals v naught times e to the negative bt over m. Box that puppy. And I'm going to pause to let you think for a moment, plus finish writing stuff down. And then I want this equation to make sense. So the original circumstance is, because the car's traveling pretty fast, there's a lot of drag force. So there's going to be a lot of acceleration. The car's going to slow down pretty quickly. But as the car slows down, it's at a lower speed, so there's less drag force. So it's going to slow down at a slower rate. And then it slows down, but it's going to even slow down at a slower rate because there's less drag force. So it's never actually going to stop. It's going to get close to stopping, and effectively it's going to stop. But if I want to make a graph of this, of velocity over time, my intercept, I start at the initial velocity, and then I have exponential decay. Okay? And once the time is a really, really, really big number, remember that a negative exponent is the same as 1 over the thing to a positive exponent. So this, when time is really big, becomes 1 over a really big number, which means it's a very, very small number. So eventually, we would say, yeah, it's come to a stop. It actually takes infinite time according to this. In math, we would say it takes infinite time, but in physics, we would say, it's close enough after a while depending on circumstances. So this b determines how steep this curve is. That's the bigger, if you remember from the original, I'll copy it down here so it's all on the screen. The original drag force equation was b, this constant that depends on the car times the speed. The bigger b is, the more drag force that is. So the faster you're going to slow down. So the bigger b is, the steeper this is going to be. The bigger the mass is, actually, the less steep it's going to be. So it's the interplay between the aerodynamics of the car and the mass of the car that determines how fast it's going to slow down. When it's speeding up, which we're going to do here in a second, but we're not going to do it with a car. When it's speeding up, that's what determines the maximum speed of the car. Okay? So, questions or comments? Okay, I'm going to copy this equation on the next page because I want to do 2 more things with it. Actually, just 1 more thing with it. V of t equals v naught e to the negative bt over m. So, just a copy. We said a moment ago that acceleration, we had to use this, is the derivative of velocity. So we can now figure out what the acceleration is by taking the derivative of this thing. So the acceleration function, we're going to keep the v naught on the front because it's a constant. And then I need to do the derivative of this exponential function. Here's one really cool thing about exponential functions. They are their own derivative. So this is e to the negative bt over m. And then I need to do the derivative of this itself. Well, you have t to the first power, so its derivative is just negative b over m. And that's our acceleration function. So if I graph this, notice it's negative. Well, that makes sense. It's in the opposite direction of the velocity. It's still an exponential decay, but we're going from a negative value to a less and less negative value. The shape graph is going to look like this. So it's the exact same shape, just upside down. And this value here, this intercept, would be negative b v naught over m. But what does that mean? What should that mean? If this was the initial velocity for the velocity function, what should this whole thing be? If this is the initial velocity for velocity function, this has to be something for the acceleration function. This is the initial acceleration. So this tells you when you take your foot off the gas pedal, this is how fast you're going to slow down. It depends on that velocity that you take your foot off the gas pedal, and then it has a smaller and smaller magnitude as time goes on because you're going slower and slower. Okay, that was part one. And I think, nah, I'm not gonna make two different videos. Part two. Now we're going to have a falling object. So, when you did the lab, we drew that there was a drag force. We are going to, for our falling object, the actual calculus example we're going to do, we're going to use the same drag force. So b, which is a constant that depends on the object falling, and v is the speed of the object at that particular time. So I'm going to drop something. It has been moving for a while. So if I draw a free body diagram, what are the forces on this falling object? Gravity down. And what's the direction of the drag force now? Up. And I'm going to draw it in between. So this is after it was released from rest, because when the velocity is 0, the drag force is 0. But before it reaches terminal velocity. Okay? So this is somewhere in between. But let's solve for the terminal velocity. What condition has to be met for it to be moving at constant velocity about the forces? The acceleration has to be 0 because the net force is 0. So for the terminal velocity, we need the acceleration to be 0, and that happens when the net force is 0. So the two forces are Fg and Fd. So their magnitudes must be equal to each other. Okay? How do we calculate force of gravity? mg. And then the drag force is this equation. I'm not going to include the negative because that's dealing with the direction. The drag force is the opposite velocity. I only want to deal with magnitudes here. Okay. And I'm going to put a t on this velocity because these two are only equal when you're doing terminal velocity, after you've reached terminal velocity. Before you reach terminal velocity, the drag force is less than the force of gravity. So we can solve this. Vt is equal to mg over b. So this makes sense, the thing I was saying earlier. Hard, dense objects don't experience a lot of air resistance because the bigger the mass, the bigger the terminal velocity they're going to reach, which means they're going to fall for longer before reaching terminal velocity. Okay? So, and that would be, if it's a small object, b is going to be small. It's a small cross-sectional area. So very massive for its size, it's a very dense, large terminal velocity. Okay, so now we're actually going to do the calculus for this situation. We want our different velocity equation, but we do know two things about its form. One, the initial velocity of that velocity equation has to be 0 because this is dropped from rest, or I'm just going to tell you it's dropped from rest. And then we know its eventual velocity has to be given by this expression because that's the terminal velocity. So I'm going to turn the page. I'm going to copy my free body diagram. So Fd, Fg, and now if I do net force equals mass times acceleration, What do I put on the net force side? What's the net force? So force of gravity minus the drag force. So the force of gravity I know is mg. Fd, the minus is showing the subtraction opposite direction. So I'm just going to write the BV. Don't get mixed up. The whole point of writing that drag force is equal to negative BV is to say it's opposite the direction of velocity. We know this object is falling down. That's why I drew it this way. Then I'll remind you, after you draw a free body diagram, whether you add or subtract, you always do positive numbers based on the directions. So we are subtracting two positive numbers. If you prefer, you can say we're adding and this one's negative. Whichever way you get to, the net force is the difference between these two terms. And then, instead of acceleration, we're going to substitute dv dt. Okay? So now we need to we're just going to switch sides. So I'm going to keep the dv here and divide by this whole thing, mg minus bv. And then I'm going to move the m over dt to the other side, so it turns into dt over m. And I'm going to do one more thing before. Is that going to be okay? No, because we've got the B. Okay. So, before we move on, I have to make a substitution. So, those of you in calculus, I know you've been doing some substitutions, but I'm going to define a new variable. I'm going to call it u. And it's equal to mg minus bv. And then I'm going to take the derivative of both sides with respect to v. So if this is a constant, it goes away, and then I just have negative b. So I can rearrange this to say dv is equal to du divided by negative b. And this may not seem like it, but it's actually really helpful. So I'm going to substitute in over here. Left side I'm not doing anything to. Instead of dv, I'm going to write du divided by negative b, all divided by mg minus bv. Well, that's what I defined to be u. And then one more algebra step. Just multiply both sides by negative b. Do you see that this is the exact same thing that we already integrated? So by rearranging this, it's the exact same thing. We're going to have a different result because of our endpoints. So when we integrate both sides, time still, we want to start from 0 and get as a function of time. So we want t at the numerator. Then on this side, I know my initial velocity is 0. And I know my final velocity is v. And I'm writing it as v on the ends because I'm not integrating with respect to v, I'm integrating with respect to u. I'm going to switch back to v before I actually evaluate this side of the integral. Okay? So, left side, I'm going to move it more to the middle, is negative bm over t. Right side is the natural log of u. We need to evaluate from 0 to t. We need to evaluate from v equals 0 to v equals v. And so now I'm going to put in, go back to mg minus bv. And now, because I've got my v's, I might as well write it. Yes. So all I did, because that wasn't quite all on the screen, I just put u, I got rid of u and went back to the original things. And now I'm going to substitute, and I wrote that wrong. That's supposed to be a v. Okay, so left side, negative b over m times t minus negative b over m times 0. Of course, that disappears. This side is just negative b over m times t. On this side, we need to do the natural log of mg minus bv minus the natural log of mg minus 0. Again, we're going to combine the natural logs, mg minus bv over mg. Now we do e to the both sides, e to the negative bt over m equals, and I'm not going to write it out this time, but e to the ln cancels out, and so we're left with mg minus bv over mg. We're getting close. We just have a couple more algebra steps, and dang it, I'm going to have to change the page. So I'm going to multiply by mg, e to the negative bt over m equals mg minus bv. And then I'm going to move bv over here, it'll be positive, and I'm going to subtract this whole thing. So bv equals mg minus mg times e to the negative bt over m. Okay, process for a moment, then I'll turn the page. We only have 2 more steps and we have our function. You're fine, it's good for you. Just think how many brain cells you are connecting and building memories and brain function. Okay.
Wait, don't
Not quite yet. Okay. It's okay.
Give me like 15 minutes.
No?
I got just this. I could probably get this done.
Dum, 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 dum. Oh boy.
No.
Okay. Here's what we will do. Is that, how much do you need? If you're still writing down, is that enough?
Yes.
Okay. So, I have BV on the left. Both of these terms have mg, so I'm going to factor. Now, if you factor out the whole thing, what's left? 1. And then minus, if I factor out mg, we have e to the negative bt over m. And then our very last step, v of t is equal, all I have to do is divide by b. mg over b, 1 minus e to the negative bt over m. Phew! We made it.
That's the equation?
That's the equation. Oh yeah, box it. Box it. All that for one equation. Now, you may have forgotten because it was 2 full pages ago, but this is the terminal velocity. So what this equation says is that your velocity is a function of time. Time goes in here. Now remember, as time gets greater, this contribution gets smaller. So as there's more and more time, you're subtracting off a smaller and smaller number. So this whole inside the parentheses is actually growing. Because more time, this term gets smaller, 1 minus a smaller and smaller number gives you a bigger and bigger number. And then you're growing based on what the terminal velocity is going to be. So after infinite time, this term goes to 0, your velocity is equal to the terminal velocity. So a graph of this is going to start at 0 and increase rapidly, and then at a slower and slower rate to the terminal velocity, which is given by mg over b. Oops, not on the screen. Okay, anybody still need the previous page? Okay. Now I do want to, and this is easy, find the acceleration. Acceleration is the derivative of the velocity. Well, this is constants. So our acceleration is equal to mg over b times derivative of this thing. Well, but that's a constant, 1. The derivative of 1 is 0. Minus itself, because the derivative of the exponential is itself, and then we need to multiply by the derivative of the top, which is negative b over m. Now, I know it's kind of squished, but do you notice m cancels out and b cancels out? And our acceleration function ends up being negative g times e. Oh, I'm sorry, it's positive g times e to the negative bt over m. And that makes sense. Good, yeah, there's a negative in the front and there's that negative. So this acceleration, when you first drop something, there's no air resistance because it's not moving yet. The only force is gravity. So when you put in 0 for this exponential, it becomes 1. The acceleration is gravity. As time increases, this becomes a smaller and smaller number. There's less and less acceleration. So if I do the acceleration graph, we're going to start from g and have exponential decay. So it is speeding up the whole time it's falling, but at a slower and slower rate. And eventually that rate is so slow that we say, close enough to 0, we have reached terminal velocity. Okay? Now, let's make sure I hit all the points that I wanted to hit today. I did. So, I am going to hit stop on the recording.